Okay, so the last speaker of our morning session is Peherstorfer from Iraq. And he wants to tell I'll let you take it over.
Thank you very much. And thanks to the organizers for inviting me here. It's been a fantastic workshop. I really enjoyed the presentations. So today I would like to talk about data sampling. You've already seen in Chauvel's talk. I'm coming from the model reduction community. We care a lot about how we generate the data from which we actually learn from. And I will try to convince you that at least the way we learn reduced models from data, it can be critical from what data we learn. So there definitely are applications where just a given data and you have to do the best you can with that data. But I would argue in many physics-based and science and engineering applications, we actually have the option to query the data and to query the data in the way we want. So that is helpful later in the learning step. Okay, let me first acknowledge my collaborators, my PhD student Mia Salmon, who has collaborated on this, and then more or less the Karen Wilcox group with Elizabeth and Forrest, who have brought up this problem and then look at it and try to solve it. Okay, so this is the motivating slide. This is kind of the wish list, what we would like to achieve. We would like to learn an interpretable model. With interpretable, I mean that we have operators in this dynamical system model, such as a linear operator, maybe a quadratic term, maybe a b that decides how the control enters. We are not really happy here with the black box function, where we feed in one time step and we get back another time step. We would like to learn a model that we can evaluate rapidly, so that we can make predictions fast. We already have seen it's typically not the end. The prediction is typically not the end, but only the means to an end. Wrapped within an uncertainty quantification loop, within an optimization loop, or some other loop that requires us to evaluate the model that we learn maybe millions of times. So we want to learn a reduced model that has a much lower state n than the state of, say, the original model from which we sample data. Now denote those quantities with tildes, so x tilde, a tilde, b tilde, and so on. Then we want to learn this model in a non-intrusive way, and non-intrusive is a classical model reduction term, which more or less means we do not have access to this high-dimensional model here. We only have, say, state data, states at time 1 to time k from this high-dimensional model, and we are trying to learn now operators a hat that are close to a tilde, which we obtain with this reduced model constructed in a classical way. Another important component for us are pre-asymptotic guarantees. So when we learn a model, we want to know in the end how good are we. And we are not necessarily interested in asymptotic results, so in the limit of unlimited data, but we really would like to say for a finite n, for a finite number of data points, how good are we, how close do we come to the actual operators that we want to learn. And finally, can we do better than the classical intrusive approach that just uses this high-dimensional system and constructs a reduced model from a purely physics point of view. And we can correct with non-Markovian terms with time delays. We've seen some of this already in Karthik's talk. Okay, so this is our starting point. We have the dynamical system. We can feed in inputs, can feed in initial conditions, and we get back an output trajectory and a state trajectory. I will in the following talk about models with polynomial nonlinear terms. I denote these models with sigma that depend on a parameter mu that does not change with time. We have the state x, we have time t, this parameter, we have linear, we have t that enters, is for the control input, and then we have the polynomial nonlinear terms with the tensors f and this xi are the Kronecker products. The output depends linearly to the matrix C on the state. And what I really would like to point out, and Steve alluded to this already in his presentation yesterday, that there are many transformations that transform more general nonlinear systems into quadratic bilinear systems and make it polynomial nonlinear systems. So while this might seem restrictive to look only at models of this form, it actually turns out that we can transform more general nonlinear systems in exactly this form. So there's no approximation at this point. It's a transformation. Now, let's for a moment assume we have given the model of the system and we just want to construct a reduced model. We have seen this way of constructing the reduced model already in Chabot's talk. Here are just the 3 steps to remind you of how this intrusive model reduction proceeds. So the first step is to construct this low-dimensional space. Could also be a low-dimensional manifold. I denote here the basis vectors with V1, Vn. N is this low-dimensional, is the dimension of the low-dimensional space. Then in the second step, there we go back to the physics. We assume here for this slide only that we know the operators of this dynamical system from which we want to learn the reduced model and project. Using here the Lurkin projection, and one could also do some residual minimization, for example, to get the reduced operators A tilde and F tilde. And then in the third step, the reduced model is constructed, and you can see this reduced model has the same form as the original model, as the high-dimensional model, except that now the dimension of the state is much lower than the dimension of the states of the original model, and that's where we want to obtain the spheres. And of course, we want that the output of the original model and the output of the reduced model are close in some probability. Now, this is the intrusive approach, intrusive in the sense that it requires this high-dimensional system. And we are now interested in, can we proceed in a similar way as this and recover this A tilde operator, this F tilde operator from data alone? So our problem setup is we impose the model structure. This is where the physics enters. Let's say we would like to learn a Burgers equation, then we know there's a quadratic term, but we don't know the exact operators. We allow ourselves to query the system, add some inputs to obtain an output trajectory and a state trajectory, and from these data now we want to learn a reduced model sigma hat from the inputs, the outputs, and the state that give us this reduced model. So we learn equations, we are not learning black box functions here, and we learn the dynamics in the sense that we can time step this model outside of the data regime that we have observed. Now there's tons of work on this. I don't go in detail through this list. Many people who are cited here actually in this room. I just want to point out we will see a close connection to dynamic mode decomposition, what we do. Of course, Steve and Nathan and many other people have worked on sparsity identification methods. There's lots of work on the time series analysis community. Another line of work that will be important for us is closure modeling. And I will describe in more detail how this will enter. Okay, so this is the setup, long motivation and problem setup. This is now how we want to approach this problem. The method that we want to use is operator inference, which is learns these operators from data. And then I would like to highlight the importance of generating the right data for this operator inference. And it will be really game-changing for us to use the right data versus other reasonable data. And finally, we can correct these models doing better than physics using time delay corrections. And then I have some examples. Okay, so this is this operator inference setting. The starting point is this low-dimensional space spanned by these columns, and then it proceeds in a very simple setting, so there's no deep mathematical things going on here. We project the data, the state trajectory x, onto the reduced space, and from this projected data x hat, we are trying to fit a dynamics model to that projected data. So we try to fit A, B, F, and C, there should be an F hat here, to this projected data to be close in, say, the L2 node. And we can do this for multiple parameters to get multiple systems and then interpolate between them. That's all. So 2 steps, projecting on the reduced space and fitting the operators in L2 sets. Now, I don't need too much to say how we solve this. I just want to point out that, of course, in the linear case, it's become the DMB operators. So what we are really interested in here are the quadratic terms, cubic terms, and higher polynomial nonlinear terms. Okay, so this is the setup. And let's now have a look on how this performs and what the problem is when we feed it with just some data that we sampled from the system and project it in the state. The problem is that the data that we actually would like to have is the data that we would generate if we had a reduced model. But we don't have a reduced model, so what we only have is this projected data. This is the time step versus the output. This is a simple example here. This is the projected trajectory. So querying the high-dimensional system, projecting on the reduced space. This is what we get in purple. And if we had a reduced model, we would time step the reduced model, we would get this green curve here. You can see this difference here. And Kevin pointed this out in his presentation. This is more or less the closure error. There's a difference between the projected data and the data that we would generate if we had a reduced model. And this is tricky for us because in this setting here, what we originally aimed to do was we try to learn this green curve from the purple curve. And there's this difference here that we have to control, and we can control this difference in principle by changing the dimension of the space. A higher dimensional space brings us closer to the green curve, but it also means we learn a higher dimensional model. On the other hand, if you want to learn a low dimensional model, which is our ultimate goal because we want fast predictions, then we run into this closure issue. So the question that I would like to address today is, can we generate data, can we sample data from our system, our high dimensional system, without knowing the reduced model, such that the error between the projected data and the actual data that we would obtain with an intrusive model is zero? And to understand if we can do this, we need to dive a bit deeper to understand where this closure modeling error is coming from. And for that, let's have a look at a very simple problem, namely a time-discrete linear system. So we have xk plus 1 is 8xk. We have our reduced space, V, that's spanned by the columns of V, and we have the orthogonal complement. And we can now split Rn into the reduced space and into its orthogonal complement, and then can at the same similar way represent the state xk of the system, the high dimensional state, as the part that lives in the reduced space, x1, and the part that's outside of the reduced space, that's in orthogonal complement. And consequently, we can write this system here as these two equations, where we have the x1 here that depends on x1 and x2 with two operators a11, a12, and we have x2, which is in the orthogonal complement, that depends again on x1 and x1 and x2. And these operators you can derive again via projection. And what's important now is that the operator that you would like to learn in this linear case is a11. This is exactly the operator that we would get with the intrusive approach if we knew the exact high-dimensional model. And the problem, the closure problem, comes now because this projected data mixes dynamics that can only be observed in the orthogonal complement with the dynamics that can be observed in this reduced space. So if we look now at our state xk plus 1 of our high-dimensional model, we project, we get x1, and we know now from the previous slide that this x1 can be decomposed in a component that's coming from the previous step of x1 and the x2 that's actually outside of the reduced space. So what this means is that this x2 introduces a non-Markovian structure into this data. So we cannot fit the Markovian model with non-Markovian dynamics. And here these plots just show how this Markovian term behaves. This is the time step, this is this Markovian term in the time delays, and you can see, oops. Oh, here we go. And you can see that it grows, it's not necessary, but the important is it has a small support. So it's not spreading all over the times, but it has a small support. And what we now like to do is we would like to generate data that in each step sets this non-Markovian structure, non-Markovian dynamics to zero. And we do this via data generation, so we don't change the method how we learn, we change how we generate the data. And we say, we first query the system to get a trajectory and construct this reduced space. And then we take this trajectory again, we take the initial condition, we project onto the reduced space, we get x1 hat. And then we query the system again, but only for a single time step. We take one time step on this projected data to get a burst of length 1. The initial condition plus one time step. And then we query again. We take the result from the previous iteration and query again for a single time step. And we repeat this until we have a bunch of bursts that all have length 1 only. And what we more or less do here is something that's done in time series analysis quite a bit, and we break the dependence assumption between the different time steps. We cancel out this non-Markovian structure that we don't want to deal with here. Okay, now we can plug these bursts, so we have many short trajectories of length 1 now instead of one long trajectory, we can then plug them back into our least squares problem. And what we can show here in a simplified form is that for a time discrete system, so that you don't have to care about the time discretization error, with polynomial nonlinear terms in a certain degree, maximal degree d, and linear inputs, linear outputs, if we have a number of bursts, k, that is greater or equal to some finite number here that depends on the dimension of the space in which you want to learn, then we exactly recover the intrusive reduced model. So the error between the intrusive reduced model we want to have and what we learn is zero after machine precision. So this is what I mean with a pre-asymptotic guarantee. So for a finite amount of samples, we can guarantee you to give you the exact model only from data without looking at the high-dimensional system, if we generate the data in this way. Of course, we need to query the system a couple of times. In principle, we have the cost of querying the system twice. First, the standard way to get to the checker to construct a reduced space, and then to query it again at each time step to cancel out the non-Markovian structure. What we can also do now with this is that since we know the residual has to be zero, we can try to find model forms and connect this to library-based methods such as SINDI, for example, to find out what quadratic term we want to use, do we need a cubic term, and so on. And the other thing that I wanted to point out, we don't need to query the original system at any random initial condition or anything like this, but all of those initial conditions we query the system at are physically meaningful. So they live in this reduced space, they are not completely arbitrary. And this is sometimes important when one has CFD codes or something like this, that one cannot just query at any initial condition. Okay, now this is just to demonstrate this visually. This is the same plot that I've shown previously, the time step output. This is the reduced model trajectory, this is the projected trajectory. And if we now do this reprojection, and we obtain this bluish curve, which is exactly on top of the green curve of the reduced model. Now, with this approach, we can recover the model that we would obtain with an intrusive approach where we need the knowledge of the high-dimensional system. We can learn this model now from data. But can we do better than this? And this is now going back to what Harding presented in the very beginning of this presentation. Can we learn time delay corrections to that model? Can we actually now model this non-Markovian dynamics that we canceled out in the first place? And the way we want to do this is in a stage-wise approach. So we start with this model, which is only Markovian. And we know that we lost this non-Markovian dynamics. So what we now would like to do is to model them via time delays. This is this delta, this is a time delay operator. And of course, again, I want to point out this has been done in similar ways in various fields through time series analysis, closure modeling, and so on. What's now our contribution, I think, is that we don't just have data and try to learn everything together, but again, we extend this reprojection to do it in a stage-wise process. So in a controlled way, we cancel out those dynamics that we don't want to learn at this point and allow only those dynamics that we can cover with our model. So we can extend, and I don't go in detail through this procedure here, but we can extend this reprojection idea that we don't have bursts of length 1, but of length k prime. This is how far we want to go back in time. Then we learn our model sigma hat 0, which corresponds to the Markovian dynamics. We then sample or simulate this reduced model for a single time step and get new data. And then we look at the difference between the data that we have queried the system, that we obtained from the system, and the data that we obtained from this reduced model. And from this difference now, we can learn those delay operators. And we know that for each of these data sets, we know exactly how this delay operator has to look like, how the model form looks like, and we can in principle set the residual again to 0. Of course, if we have higher order non-polynomial nonlinear terms, there might interactions show up, and this grows exponentially in some sense. We are mostly interested in here later on in linear time effects. Okay, let me show some numerical results on this. So we have seen already many times the Burgers equation. It's also my standard benchmark example here. The spatial coordinate is omega. It's a bit of a strange notation. I apologize for this. T is time, mu is the parameter, which is here the viscosity in front of the diffusion. We have the boundary conditions where the input now controls this boundary condition, and the rest of the setup is pretty standard. Here's the solution, spatial domain versus state at time step 1000, and I can time step this up to time step 10,000, and you can see there slowly starts to be some shock formation, but we are not there yet. So in this first part of this example, there's no real shock formation in the classical sense. So what we do now is we sample this system at to obtain two trajectories for 10 different equidistantly chosen parameters in this parameter domain. This is our training data for those who learn the reduced model. And then we interpolate between those reduced model operators at new parameters and evaluate and simulate those interpolated models to predict the behavior at new parameters and at new inputs. So it's what all the errors that I present are for test data in terms of the parameter and different input from what we have seen in the training phase. Okay, first again to convince you that we mirror the system only at physical or meaningful initial conditions. This is time versus the output, and you can see here on top of each other more or less the full model trajectory, the projected trajectory, and the reprojected trajectory. They are different, but one needs to zoom in. So what I would like to convince you here of is that we query the system only at states that are physically meaningful. So we don't need to query the system outside of nominal conditions, for example. Okay, this is now the error plot. This is the dimension of the reduced model that we learn and that we benchmark against. And this is the average relative L2 error of the states. This is the curve that we get when we have everything given. If the high dimensional system is given and we just construct a reduced model in the classical way. This is what we want to recover. This is what we get if we just apply this operator inference naively on the projected data. It does well maybe in the beginning, but you can see that already here we have quite some error and it becomes unstable for the rest of the dimensions and we cannot get a reasonable prediction. Now if we apply the same approach with the reprojected data, what we would expect is that the new curve is on top of this black curve, because I claim that we exactly recover the intrusive reduced model, and indeed you can see that this purple curve now is exactly on top of this black one. So with this way of generating the data, with a finite amount of samples, we can recover the reduced model. And this goes back to the pre-asymptotic guarantees that we can make. Now I also talk about time delays, so let's learn some time delays. One reason that we want to learn time delays is because we only have partial observations. So let's say we only observe 50% of the states. This is maybe in a hyperreduction case or in a discrete empirical manipulation case. And we want to make up for these partial observations by learning now time delays in our model. This is the corresponding error plot. This is the number of delays. So from no delay up to 20 time delays. These are all linear delays. And this is the average relative L2 error in the states. This is the intrusive model. If we only have 50% of the states, then we cannot really push forward the dynamics, even with the intrusive reduced model. We get a complete nonsense. There's a relative error of 1. This is the best we can do by projecting into the reduced space. We cannot do better than this projection error here. And the green curve is this inferred model. Start here, no delays, we recover exactly the intrusive reduced model. And as we keep adding delays, you can see that we achieve lower errors, maybe up to say 5% compared to a relative error of 1. And these are all in the linear delays. Okay. Now here comes the setup with the shock formation. So we change now the problem a bit, have different viscosity parameters, different time stepping, and so on. On the left, you can see the ground truth, the system we query. This is space versus time. You can see how the shock moves here through the spatial domain. And on the right, you can see the results for intrusive reduced model. And you can see this oscillatory behavior here. And this is an error because of the approximation in this reduced space. Now, here are the results that we obtain if you learn now the model and learn it together with time delays. This is time versus the shock position. This is the inclusive reduced model. You can see I applied here a standard shock position detection tool from MATLAB. You can see these oscillations confuse the shock detection quite a bit, and it does not really a good job in detecting the shock. This is the error, in the average error in this shock position. You can see we go here to dimension 60 in that model. The error goes down, but the 60-dimensional reduced model is already quite big. Now, if we learn the model from data, we said we exactly recover the inclusive reduced model, so we cannot do better than the inclusive reduced model here. Again, purple is exactly on top of black. But if we now learn the time delays, if we do closure modeling following Kartik's work, for example, then with 4 time delays, you can see already visually here that the shock position is captured much better than without the delays. And also in terms of the error, you can see that the error decays faster. And also learn 8 delays, get a little bit of faster decay here, and just looking at the plot, you cannot really distinguish between 4 and 8 delays. Okay, finally I want to show this example just to convince you that this does not only work for burgers, but also for other examples. This is Chabet-Infante equation with a cubic polynomial nonlinear term. You can see here this oscillatory behavior over time. I don't go in detail to the setup here, but more or less we reoriented the high-dimensional system and learn from that high-dimensional system the model exactly. And this is again shown in this plot here, the dimension versus the relative L2 error. This bluish color is when we learn naively from the projected data. It does not give us a reasonable reduced model. And again, black and reprojected learning on top of each other, you can see we recover this reduced model. Okay, with that, let me conclude. So the goal is to learn interpretable models, interpretable in the sense that we have operators, that we can look at the eigenvalues, for example. We want to learn reduced systems of equations so that we can predict rapidly. Again, because the goal is that we rock this within a design loop, that we rock this within an optimization loop, and certainly quantification loop. There we need many evaluations. In this setting here that I described, it was really key to generate the right data, not only to decide where to sample, as a lot of model reduction literature is looking at, but how to sample it, to cancel out this dynamics that we don't want to cover in this first reduced model without any time delays. I also try to convince you that we need pre-asymptotic guarantees, so not asymptotic ones, but guarantees that hold for a finite number of sample sizes. And of course, this is a big topic in machine learning anyways, but in this setting we could recover something very similar in a quite simple setting of this approach. Several references are on my website in case you're interested in this. And with that, I thank you for your attention and I'm happy to take questions.
Questions from the audience?
Does the guarantee apply in the case of any noise?
Well, if you have noise, then it would show something like an expectation. We have not done the analysis, but that's something we're looking at. If you have unbiased noise.
So you assume the polynomials, and you assume a dimension L. Is that kind of like the library you're picking, as it were? Or?
That's the model frame. So right, that's a good point. Thanks that you bring this up. So we can approach this in 2 ways. First, we can say this is the physics we bring in. Say if we want to learn Berg's equation, we know there's a quadratic term, so let's put in a quadratic term. The other one is we could couple this, say, with something like SIMD, sparsity identification type thing. But then also, if we generate the data in the right way, we know that the residual in the end has to be 0. So we can keep adding terms until the residual is 0. And then we know we have the right model frame, or a too-rich model frame.
So adding terms meaning?
Higher order terms.
Okay, so you start with a certain L, and then
Yes.
you just keep raising L until you're at that. Great.
So what's the computational expense difference as you increase delays? Like, so obviously your 8 delay is better, you know, you would just say delaying, but of course then you're getting a bigger matrix, right? So, I mean, like if you were to think about an error versus computational trade-off, how does that look?
Okay, so I think we have to look at the offline and the online phase. So offline, we need to query the system more times because we need, again, this reprojection for each delay separately. We need to do a learning step separately for each delay. Online, we have only linear time delays, so I would say they are very cheap to evaluate. One has to store some of the previous time steps, of course. That might be a problem at some point. And as soon as you go to interactions so interactions between different time steps, higher order, or even more general models you could fit in principle, and Kamlik has done is a neural network with those time delays, then things of online cost really become a problem. But I think in the simple setting that we looked at, I didn't see much difference in terms of runtime.
Any other questions? Okay, well, let's thank Ben again.